Today we have Bruno Schuler. It's very nice to have you here. Thanks for coming. And so for those of you who don't know Bruno, he studied at ETH in Zurich and then carried out a PhD with Leo Gross at the IBM Research Lab in Zurich. After graduating in 2015, he stayed at IBM for a bit and then moved on to the Lawrence Berkeley National Lab, the Molecular Foundry, as an SNF postdoctoral fellow, and then later on as a junior group leader there. And what was he was doing there? He was working on defect-based quantum emitters in 2D transition metal dichalcogenides, and also developing the high-resolution imaging facility at the Molecular Foundry. And he has now recently, earlier this year, returned to Europe, to the EMPA, the Swiss Federal Laboratory for Materials Science and Technology, where he is at the Nanotech at Surfaces group. And he's going to be working on low-dimensional quantum materials and with cross-correlation microscopy at the ultimate spatial energy and time resolution. And Bruno also received the ERC grant this year on atomic quantum emitters in 2D frameworks. So I think with that, it's very nice to have Bruno here today, and the title of today's talk is Probing Atomic Quantum Defects in 2D Semiconductors. So please, the floor is yours.
Thank you so much. Let me bring up the slides first. Okay. All right, so thanks so much for the introduction. It's a great pleasure to present my work on this beautiful colloquium series that you guys put together. And I think it's really something that many of us appreciate a lot, that you're doing this in the community. And I'm happy to hear that it will also continue next year. So I'm really looking forward to this. So today I would like to give you kind of an overview on our work on atomic defects in two-dimensional semiconductor. And as Peter already pointed out, I relocated earlier this year to EMPA, so actually to the team of Roman Fasel, Oliver Gröning, and Pascal Ruffia, that most of you will also know from their very nice work on GNRs. But there we'll also continue this line of research on two-dimensional material, actually. But most of the things I will show you today is will be, or basically was carried out at my time still at the Berkeley Labs. So let me start first with two kind of generic examples why you should, or everyone should care about defects in semiconductors and why this is an interesting technology actually to develop. So on the left side, you see a typical plot that you can find in many textbooks where you plot basically the resistivity of silicon as a function of the doping density. So in silicon, chemical doping, so introducing different species into silicon to change the conductivity, has been really keeping silicon in business for a long time. So a lot of development has went into making this silicon material very, very pure, and then introducing in a controlled manner foreign atoms like phosphorus or boron, for instance. But if you look at the x-axis down here, you really see the kind of precision that is necessary to do those. So we are really talking about parts per billion. So 1 in a billion atoms is a foreign atom, or up to 1 parts in a million or so. So this is really a typical range, and that's just very hard to copy for other materials. So that's why silicon is still kind of in business today. Now, and kind of different concepts that people start to think more recently in these days is how to use another degree of freedom, actually the electron spin of an individual atomic defect in diamond, for instance, where NV minus center has been looked into very, very heavily. And there the idea is really to harvest the quantum property of a single spin, for instance, by doing coherent manipulation by electromagnetic fields and then having optical readouts and so on. And I think for 2D materials, both of these established concepts will kind of have a new twist, because 2D materials are in a few ways quite different from their bulk analogs. And this should kind of be illustrated in this very basic cartoon. So on the left side, you see just kind of individual dopants. Here, this red guy should be dopants, and the orange one should be electronic wave functions. So in ordinary bulk semiconductors, the wave function associated with dopants spend or spread across like tens of unit cells normally. and they have, like normal shallow dopants, have a binding energy of a few milli-electron volts only. So they can be excited by the thermally and so on. Now in 2D materials, the picture is a bit different. And the reason for this is because in 2D materials, the effective mass is larger in general, and the dielectric screening is much smaller. So this leads to the fact that the electronic wave functions are much more confined now. So typically, most of the defects in 2D materials are deep defects, and their binding energies is more on the order of a few hundreds of milli-electron volts. So about a factor of 100 bigger than in bulk semiconductors. And this bigger characteristic energy scales is also the reason why you have quantum properties that are visible or kind of appear even at elevated temperature, and they're fairly robust. Now, there is another cool aspect about 2D material, and this is that you can tune them on a quite big range, for instance, by electrostatic gating or also by changing the substrate. So they are quite flexible in terms of how you can tune those by external means in certain ways. Also, they form very nice and beautiful interfaces with other materials. So for instance, what you don't have in many 2D or van der Waals materials is that you don't have a lattice matching requirements. So we can grow these things epitaxially on each other without really having the need to have the same lattice constant, for instance. And that's something which is different in bulk semiconductor. Moreover, like many of us are in kind of the scanning probe business, so the nice thing for us is that the whole material is really accessible. So everything lives on the surface. So surface sensitive probes have, there are cool ways how to interrogate this system and the whole system, not just the surface of it, because just simply everything is surface. Now the material class that we have mainly looked into is transition metal dichalcogenides. So in this trigonal prismatic geometry that is depicted here on the left side, they adapt this kind of hexagonal shape if you look from the top. And they're basically consisting out of transition metal, which is sandwiched between two layers of chalcogen. Now, if you look at the band structure, so in their bulk form, it looks like this. So you have apparently a band gap, of course, and you have an indirect one at that, and then you have states at the extrema, on the band extrema, which are mainly composed out of sulfur p orbitals. Now, if you go down to only a single layer, shown on the left side, so there's few things which are changing. So first of all, the band gap gets quite a bit bigger. It becomes a direct band gap as well. And then the states are mainly, the contribution of these extrema states are mainly composed out of d electrons of the transition metal. So states which have a kind of high orbital momentum, and that's why, for this reason, spin orbit coupling becomes quite more important. And there has been a lot of excitement about these materials, especially in the optical community. Because of this strong spin orbit coupling, it is now possible to address different types of your Brownian zone, for instance, K or K prime point, by selecting the helicity of your incoming photon, essentially. So because the spin and the Valley degree of freedom are now coupled to each other. What our research is mostly concerned about, however, is really how to design this band gap in this 2D material by introducing dopant, which then have themselves discrete energy states, which may be spin polarized, and then really play around with these states. And in the long term is really we're trying to coherently control their properties and the excited states dynamics of these states. But the first step is really trying to understand what type of defect create which type of energy manifold, and kind of select the more interesting one from the ones which are kind of just detrimental to the material. Then something which is particularly nice about TMDs is that you do not only have the cool physical properties which mainly arise from the strong confinement, but you also have a quite versatile chemistry. So today, I think more than 60 binary TMDs have been synthesized so far, and I think by now it's even more than this. And there is just a lot of different combinations that you can think of. So just the sheer amount of transition metals that there are there and chalcogens, you can combine these elements with each other, and they give new types of variations of materials. So that's what makes them quite flexible. So we looked into these materials with different scanning probe methods, and I think I don't need to go into too much detail what they are in this audience. So we used CO-tip and CAFM imaging to look at at which atomic sites these defects are located, essentially, and then STM and scanning tunneling spectroscopy to look at the defect states to really map out the defect orbitals, and then STM luminescence as a third technique to more investigate optical properties of individual defects. So these are the things we are talking about during the talk. So the further outline of the talk will look at follows. So first of all, we are going to discuss what kind of defects we find in the as-grown material. So really without doing anything, so just by the synthesis, you already have a few impurities that end up in material. And we spend quite some effort in trying to understand what they are. So that's really something which is not that trivial as you may think. So that will be the first thing. And then we look how we can controllably introduce those defects by different means. For instance, by some thermal annealing, by chemical doping, through atomic manipulation, but also through some lithographic means. Then we pick one example, which shows some very interesting states. That's something we call the carbon radical ion, which we just recently put on archive. And then one instance where we could drive electromagnetic excitations at individual point defects in these TMTs. So that's kind of an overview STM image of how a typical sample may look like. So that's tungsten disulfide grown, one flake of tungsten disulfide. So that's a rather small island here, grown on graphene on silicon carbide by CVD. And we were very lucky to have good collaborators here that grow these samples for us. Especially I want to highlight the groups of Josh Robinson and Maurizio Terrones from Penn State, and Christoph Kastel and Alex Hohleitner from the TU Munich, that are really excellent collaborators that help us growing in a targeted way these kind of TMD samples. So you see also here that we looked into different type of growth methods. So with CVD, MOCVD, and MBE, but also exfoliated samples. So we figured out how to make them clean enough that we can look at them and really fulfill this high surface cleanliness requirements of a scanning probe, even though these materials, of course, were transported through air and everything. So I think this has been a very important step. Now that's again the kind of overview of the things we see in just as-grown tungsten disulfide. So in the first row, you see an STM image of individual defects here at positive bias. That means the empty states close to the conduction band. And here on the bottom part of the very same defect in a CO-tip AFM image, where you can essentially see the sulfur atoms in the top layer here. So these are these red guys, but we also know the location of the tungsten atoms because in one of the sites, this looks a bit darker. So we know that this is actually the place of the tungsten. So from this, we know which site these defects are sitting. And what we observed is that there is a lot of substitutional defects. For instance, oxygen substituting for sulfur is a very abundant one, and we see those very consistently throughout all the samples, grown in different ways. And it's just a defect which has a very low formation energy. And oxygen, of course, is also a chalcogen itself, so it is just from the chemical kind of intuition, it makes sense that this is also a very low energy defect to form.
Sorry, Bruno, there's a question
Yep.
from Ingmar.
Yep, sure, go ahead.
Hi, Bruno. Sorry to interrupt.
No worries.
You mentioned that you do CO-tip AFM. Do you pick up the CO from the tungsten diselenide or from the graphite? Where do you get it from?
That's a good question. So no, we prepare the tip on a gold 111 surface, and then dose the CO also to this gold surface, pick it up there, exchange the sample, and then land again on the tungsten disulfide. And the success rate is fairly big. So I think more than 50% you keep the CO on the tip.
And you mentioned that you grow the samples on the East Coast and then you study them in an ultra-high vacuum system on the West Coast. There were no issues with oxygen degradation in the meantime, or did you use a vacuum suitcase, or how did you transfer the samples?
So the transfer was usually through air. So that means it could oxidize, but however, we also looked at samples which have different ages. So like say from the time scale of hours. So Christoph was actually working with me at the Berkeley lab. So we also looked at samples which were immediately transferred in our UHV, and there was not a big difference in terms of oxygen concentration. So we don't think that will happen over time in most of the materials. So there is a few materials which are more air sensitive, of course.
Okay.
For tungsten disulfide, not so much.
Okay, thank you very much.
Sure. And sometimes we also cap them with selenium. So for instance, molybdenum diselenide, which was grown by MBE, we capped them with a selenium layer and then removed it in UHV. Okay. And also those show the oxygen.
Very
defects.
clear, thank you.
Okay, thank you. Okay, so and then the other type of defects we show, we see frequently is transition metal substitution. And this simply comes from the precursors, so they are not 100% clear, but they have impurities on the order of parts per million, and this also just ends up in your material. So for instance, chromium or molybdenum replacing a tungsten atom. And this one here, we talk a bit later, which kind of has a funny STM image, looks like a dark hole. We actually could assign to a carbon type of impurity. But now how we really come up with these assignments, right? This is really not something which is immediately clear and should be illustrated on this side on the example of chromium at a tungsten site. So what we essentially do is like we record all the data we can with the STM and AFM, do spectroscopy especially. This gives us the kind of fingerprint of these states. So for instance, chromium has 3 states close to the conduction band edge, which is labeled here 1, 2A, and 2B. We can map out how they look in real space. We can record an AFM image to really see that it is a tungsten site defect. And then sometimes we even observe strain, so kind of a local contraction of the sulfur atoms. And then we try to make an educated guess what these things might be. We perform ab initio theory, and by me, I also mean collaborators of us, especially Xunho at the group of Jeffrey Neaton in Berkeley. It's very helpful in doing so. And then we can compare, and then we see all the evidence we have and try to see whether we have a good match or not. And usually if it's not a good match, it's very clear. For instance, the electronic states are completely different. The spatial kind of orbital shape doesn't match and so on. So when we have this really full agreement, we can be extremely confident that the assignment is actually correct. Now, something which was quite peculiar to some of these defects is when they are charged. So when they are charged, they do not only show orbitals which are associated to chemical orbitals, but in fact also hydrogenic bound states. And this should be shown here. So this is a negatively charged defect, so this carbon defect. But at that time, we did not even know what it was, but just a negatively charged defect. And how you can see this is at the positive biases. So the conduction band is bending up, so it's repelling the electrons in the conduction band. But on the other hand, this negative charge is an attractive potential for holes in the tungsten disulfide. So it localizes holes. And these states actually even look like prototypical hydrogenic states. So they have S-like and P-like wave functions. And then together with the group of Johannes Lischer at Imperial College London, we can model this with a very simple tight binding model by in fact just assuming a point charge. And already this very simple model gives us a very good correspondence of what we see. So they could model even the STS along the line here and all the states. And it turns out that these states do originate from different band maxima. So you have, and it's also what you expect, you have this S and P-like state that emerge from different band extrema, like at the KM and gamma point. So we can kind of assign through this, again, in collaboration with this theory modeling, we could assign where this wave function actually come from and why do they appear and why do they have such kind of binding energies, which are quite significant again. Okay, so these are kind of then the 4, I would say in a very simple fashion, a cartoon fashion, 4 defining things. So to really predict what kind of energy states you might expect in your band gap. So first of all, very obvious, crystal field splitting. So how a certain impurity is coordinated in your lattice. You can already figure out from some simple group theory arguments how many defect states you would expect. Spin orbit coupling is very important in these materials, not surprisingly. And electron-phonon interaction is very important too. We will come to this more towards the end of the talk. And as we have just seen before, charge localization is very important. So let's move on to the second topic, the controlled generation of point defects. And let me start with an example, which I think is somewhat controversial in this 2D materials community. And this is the influence of vacancy defects in these materials. So many of, especially optical signature of which people attribute to the kind of presence of defect, has been assigned to sulfur vacancies or to chalcogen vacancies in general. And that's something we expected to see in our sample a lot. And we also thought they would be there. So first of all, this oxygen one, which looks like this. So the oxygen substitution pretty much looks like a vacancy in AFM. But then we did some annealing in ultra high vacuum, and then two different types of defect arise, which we could assign at the end to this vacancy in the top side and vacancy in the bottom side. And they have completely different electronic properties. If you compare now the oxygen substitution, which we see a lot in all our samples. So they essentially have a very boring SDS, so essentially no defect states in the band gap. And then if you look to the same spectroscopy at a site, which we now know is a vacancy. And these things really only appear after you anneal them to extremely high or quite high temperature, a few hundred degrees in vacuum. So you see these two very clear defect resonances, which are followed by some Vibronic sidebands. And we know from the modeling that this is in fact is 100% consistent with the presence of vacancies. So that means, however, if you anneal it in UHV at very high temperature, you can selectively create sulfur vacancies. Then another thing we have tried in collaboration with the Hohleitner group in Munich, and Elmar Mitterreiter was actually coming to Berkeley and doing these measurements together with us, is to bombard, in this case, molybdenum disulfide with a helium ion beam. So to really try to lithographically define defect patterns. And that's what should be kind of shown here. So here Elmar actually wrote lines with a certain spacing. I think spacing should be 20 nanometers or so. And we could indeed see that in certain direction, we have this kind of line looking kind of thing. So here the kind of problem is that if you have create a lot of defect, also your adsorbates, so this is this white stuff here, they also like to hang around there, and it's kind of hard to get rid of. But I think convincingly we could see that there are lines, and we can also determine the lateral spreading of these lines because of some backscattering effects from the helium ions. And we could understand what kind of defects are forming in these material with the helium ion beam. So it's predominantly sulfur vacancies, but there is also other things which are sometimes even a bit more complicated. Now,
can I ask a question on the previous one?
Yes.
So if I look at your schematic, it looks like you suggest that you only peel off the top sulfur layer. Is that the schematic, or it doesn't really look like that?
So the schematic here on the right side, you mean?
Yeah.
No, we find both things. So so we see sulfur. So that's actually a top one, and that's a bottom sulfur vacancy, among with other things. So this, I think, the scattering cross section might be pretty similar, I think, between top and bottom. So there shouldn't be too big of a difference. But it's quite a bit higher than if you compare it to a transition metal. So forming a transition metal vacancy, it's much harder for the helium ions.
All right. Yeah, thanks.
So we see both things again. Now, something we have looked into more recently is to use kind of bottom-up synthetic means. So to introduce different transition metals during the growth of these materials, such as, for instance, rhenium. So here, our Penn State collaborators introduced rhenium dopants into this material, and here it's very nice because you exactly know what you put in there. So the assignment, of course, is then almost becoming trivial if you compare it to the ones which we don't know a priori. We can do again also the FT. We see a beautiful match between the chemical defect orbitals and the ones which are calculated. We see because rhenium has essentially nominally one electron more it is expected to be an n-type dopant, and it's also what we see. So we see it has states close to the conduction band, and in this case it's actually positive, so it's ionized. So because this state is getting depleted because the electron can simply leave to the graphene substrate. So we see n-type dopants which are positively charged, and we see p-type dopants which are negatively charged. So I think that's also something cool to play around with. So this goes pretty much in the same direction as some concept of the chemical dopants. Of course, again, here, still everything are really deep dopants. So how useful this is for really changing the conductivity is another thing, because again, all these wave functions are quite localized. And then similarly to this introducing by bottom-up means these transition metals, what we did is exposed then this tungsten disulfide layer to a methane plasma to introduce carbon dopants. And as you can see quite easily here, there is quite a drastic change if you do this. You see a lot of these negatively charged defects. So these are all these dark looking things, so that you can change the concentration from about tens of ppm, which you just usually have due to some impurities, to something which is more in the range of a 1% defect concentration. And here in this case, we actually used this to assign what this dark defect was, because this was a kind of a tricky one to assign. But now knowing that they did this methane plasma treatment and that we see this defect all over the place, we could assign it to this carbon hydrogen complex, and also the AFM1 kind of makes sense if you simulate it with the code developed by Pavel. So, and now we will kind of stick to this defect for a while. So, and because there is some other aspect which is quite interesting to it, and this is we can remove the hydrogen atom from this carbon hydrogen complex. So we start out with this carbon hydrogen that we can implant selectively through chemical means. And then we use our scanning probe tip and apply a high bias and a high current to it, so we can kind of peel off this hydrogen atom. This is quite a selective and very reproducible process, so you can go one by one and you see only this type of defect changes from this dark looking thing to something more which looks like an orbital. You can also do this on a bigger scale by just like going around with your tip at high bias and do this all over the place. So, and how do we know this is actually that we remove the hydrogen? Why is it not simply a vacancy and so on? So this should also be, again, this is the kind of the electronic signature, or the electronic kind of footprint that really tells us what is happening. So if we go first again from this carbon hydrogen complex, which is negatively charged, so we see all these hydrogenic states, but other than that, no states in the band gap, which is expected for this type of impurity. And then during the voltage pulse, we see that two new resonances emerge. So one in the unoccupied states and one in the occupied one. And then if you look at the kind of a cross section here, so just at a single spectrum, we see the same thing. And there is even like a more sophisticated kind of subband structure here. So there is this equidistant peak, which we in fact assign to Vibronic sidebands of these electronic states. And if you map them out in the negative and positive bias, you see that they look fairly similar. So we attribute this actually to a singly occupied defect orbital. So we can call this kind of a negatively charged carbon radical. Now you can do the same thing also for tungsten diselenide. And there the picture is slightly different. So first of all, if you start out with CH, also this one is negatively charged, but now if you remove the hydrogen, this thing becomes neutral. So we see this, for instance, up here in the conduction band, so there is no band banding anymore. And you just have a single state, which is now completely unoccupied. So it looks fairly similar, but again, you just have one state and there is nothing here. And we attribute this just to a to a non-occupied kind of dangling bond-like state of this carbon impurity. Now, doing the calculation, it turns out that the singly occupied defect orbital is spin polarized, and the energy gain you gain from this doing the spin polarized calculation is on the order of about 100 milli-electron volts. So it's quite significant. And that's how the kind of spin looks like. There is a small magnetic anisotropy also that tries to force the magnetic moment out of plane. So it's very much localized at the carbon center itself. And because you have now a magnetic moment and you have the spin polarized defect states in the valence band, you also see a slight lifting of the degeneracy of your K and K prime values as kind of a side effect of having this local magnetic moment. Now, these are the Vibronic excitation spectrum, which I mentioned before. And here, I think it's quite interesting how these compare to each other. So how these unoccupied state and the occupied defect state kind of react towards if you populate this by an electron or hole, and how this basically the atomic lattice reacts to this electronic excitations. This is shown here on the top one. So for one monolayer of tungsten disulfide, you see that we see this kind of repeating pattern. Here are the values given. So we see one strong resonance at about 25 milli-electron volt with a Young-Rees factor, which kind of quantifies the electron phonon coupling on the order of 5. And here for the occupied one is different. So first of all, we see different modes which become more dominant, and we see that the Young-Rees factor is a little bit smaller. But this really tells you that there is some sort of spin phonon coupling going on, because again, we have this spin polarized states, which are quite similar in terms of their wave function or their spatial wave function, but they carry different spins. So this react differently to the lattice reacts differently to those. And also if you compare two monolayer to one monolayer, there is quite a significant difference. So first of all, in general, the Young-Rees factor gets smaller. And this is simply because now in two monolayer, your wave function is a bit more delocalized. So you expect that the phonon coupling is a bit smaller, and also your resonances become sharper. And we think this is simply a lifetime effect. So because now your electron spends a bit more time in your defect before it kind of drains down to the graphene. And this is also consistent with density functional perturbation theory calculations that we did. It could reproduce what kind of phonon modes, which are mainly contributing, especially these breathing type modes, which kind of involves the carbon, the opposing sulfur, and the tungsten neighbors. But also then the carbon oscillation, which is especially, so this is at more at higher energy, so more on the order of 70 to 80 milli-electron volts. And this is especially important for the occupied states. We don't see that it actually for the unoccupied ones, which is also consistent with the calculations. And there is also this resonant mode, so a bit more delocalized mode, which is more important for the occupied states.
Bruno, sorry for interrupting. There's a question in the chat, which is how do those peaks behave with temperature?
So we didn't do any temperature dependence, unfortunately. So I can't really say anything about it.
But how then you are so sure that they are due to vibronic or phononic states? What are, yeah.
So I think the main confidence, first of all, comes because they just really behave like their evolution. If we try to kind of generate this spectral function, it really much kind of can be described by a Frank Condon type picture. So if you just consider a few modes, like this one can be described by 3 modes, and this one by 4 modes also, can pretty much kind of reproduce this STS spectrum. But for sure, also the temperature dependence would be an important indication. Now, second, why we are sure is because of also this calculations that we did. It just perfectly describes these peaks that we are seeing. Also, the magnitude is kind of in a similar range that we are seeing from experiments. So I think it's mainly these 2 factors. Now, changing, I mean, what you're suggesting is essentially, can't we change the phonon occupation by changing the temperature? And there is just also some limitations what we can do experimentally. So for instance, if you significantly want to change the phonon population or like at the thermal distribution, you would need to go to room temperature or so. So room temperature is like 25 milli-electron volts. And even then, the change in population would be not that drastic. So it would be hard to see. plus working at room temperature and keeping that kind of atomic resolution is just very, very difficult to do.
Yeah, actually it was about the lifetime of these phononic states. And that's if some of them are long lifetime, so they probably have some selectivity toward some of them. And so when you raise the temperature, probably some of them will be more occupied than others. That's exactly what I wanted to ask, and how they implicate the spin phonon coupling afterwards. That's basically.
I see. Yeah. I see. Okay, so I mean that's something we can for sure try. I just didn't expect too much to happen on a kind of a reasonable temperature scale that we can access, but it's still something we can try for sure. Thank you. Okay, so this should just kind of summarize this part. So what we can do is we can do a selective hydrogen depassivation by our scanning probe tip, then have this dangling bond singly occupied by donating, basically the graphene donates an electron to this dangling bond. It becomes spin polarized, and we also studied in detail the vibronic coupling at this defect. Now, last part, how am I doing in time, Peter? A few more slides.
Oh, yeah, no problem. You've gone about 35 minutes, so you have 10 minutes.
Okay, cool. Excellent. So the last part will be about where we try to induce electromagnetic excitation and looking at the optical kind of response to this. So that's kind of a simple cartoon. So what we did is, again, we parked our tip on top of a defect. In this case, we picked the sulfur vacancies that we created and then injected at kind of higher electron energy, so higher voltage essentially, and look at then the photons which are emitted in the far field. And by doing this, we could really record a kind of what we call photon map of a single defect. We see this has nothing to do with the topography or anything, or the AFM, of course, but this is really something where we can do an optical excitation of this junction. Now, it took us a while to understand what was really going on and what the mechanism is. So there is a few kind of competing models which that try to describe how this STM luminescence work. And I think it's also specific to the type of system that you're studying. Like in our system, the explanation, what we come up with is that our electrons, most of the electrons, as in normal STM, will tunnel elastically to our, let's say, if we apply high bias, they will go to the conduction band and then drain eventually to the graphene. But some of the electron undergo an inelastic transition. So from some state in the tip, which is a continuum of state because it's a metal, to our discrete defect state that lives isolated in the band gap essentially. And this transition becomes more likely if the photon density of state at this frequency, so that energy difference that connects your initial and your final state, is high in your cavity. And the photon density of states is mainly, in our case, is mainly composed of our plasmonic tip. So because we kind of poke our tip into the gold first, we will have a gold coated tip. And this kind of defines the emission energies which we are likely seeing. And that's actually also the case. So if you look now at the photon energy that is emitted as a function of the applied sample bias, we see a few things. So first of all, we see a clear emission onset at a certain energy, which scales linearly as a function of the applied bias. And there is two of these onsets, which we assign to the two defect states of this vacancy in this case. So this depends on what kind of defect states you're probing. But there is quite of a broad, which people would normally describe as a plasmonic type of emission. So fairly broad emission, but still we are just looking at a single defect. So the question might arise like, why is the defect not more narrow in terms of spectral bandwidth? And the reason is, again, because we have here a continuum of states. So not only can your electrons tunnel from your Fermi level, but also more down here. So they tunnel with different probabilities, depending, of course, on your tunneling barrier, but again, also this photon density of states. And just in the spectral range here of the gold plasmon, we see a strong enhancement. So this is like a Purcell enhancement of your plasmon that is mainly localized at your tip. And this +1 also helps to mediate the coupling from the near field to the far field where we actually detect these photons. So that's kind of the summary of the talk already. So I hope I could show you that indeed these 2D semiconductors are a quite nice and versatile platform to kind of engineer and probe atomic quantum systems. We looked at atomic, electronic, and optical properties at individual defects measured by different means using scanning probe methods. And we characterized in detail what are different types of impurities already present in synthetic defects without doing anything to them. So that's just a fact how they are. But then we also try to find different ways how we can controllably and selectively generate those defects by, for instance, by annealing, chemical doping, atomic manipulation, and helium ion bombardment. Then we kind of identified an interesting, very prototypical spin 1/2 defect, which is what we call carbon radical ion, that we can generate also selectively. And we looked into some more the kind of optical properties of single defects. And with this, let me thank a bunch of people, which of course were very important to kind of make this work happening, especially Catherine Cochrane, a postdoc that worked together with me in Alex Weber-Bargioni's group at Berkeley, Elmar Mitterreiter and Alex Hohleitner and Christoph Kastel from TU Munich that worked on this helium ion defect samples. Then people from the Robinson and Taronis group at Penn State who were very helpful in synthesizing these materials. Theory collaborations from Neaton group together with Xunho Lee, and Johannes Lischner that performed this kind of type binding calculation for the charge defect, and Javier Garcia de Abajo, which helped us to understand the light emission at defects. And maybe already also some advertisement for my upcoming ERC grant that will start only next year, unfortunately, but I would already try some kind of premature advertising. So if you think that's some cool stuff and you will like to work in our group and as a postdoc or PhD, come and just drop me an email. That would be cool. All right, thanks everyone for the attention.
Thank you, Bruno, for this really wonderful talk. So now we have some time for questions. So if you have a question, you can either write it in the chat or you can raise your hand in the participants button. So there's a question by Leo. Leo, please go ahead.
Hi, Bruno. So my question is, can you extract the lifetime of these states on the top and bottom layer, and what order are they?
So there, I mean, we could. So, and it's also what we did just from the broadening. So if you assume the entire broadening comes from, is due to lifetime limiting. So this is on the order of, in the case of 2 monolayer, it's about 200 femtosecond. So if you just think about the distance where the defect states and the graphene has, and you just model this by just a vacuum or so, that's also more or less what you would expect. You would expect probably a bit a longer lifetime, so we are not sure ultimately if a fraction of our broadening still comes from coupling to low energy acoustic phonons. Because also the shape of these things, we modeled them by a Gaussian and not by Lorentzian. So this gives us a better fit. So at the end, it's on the scale that you might expect just from the sheer distance between defect state and graphene, but then the kind of the shape as a Gaussian tells us there might be some contribution from low energy acoustic phonons that contribute.
Thank you.
And there's a question in the chat by Tsipe, which is, did you check the G2 of the electron stimulated photon emission at single defects? Yeah, whether they are single photon emission, and what is the difference between your electron stimulated photon emission and the traditional photon emission process? Okay, that's an interesting question. So we tried. The problem is if you just look at the counts. So we are working on a substrate which is not plasmonic. It's graphene on silicon carbide. So the count rates that we get are just very small to do a G2 measurement. So we tried to set it up, but then the photon statistics were not enough to do a convincing G2 measurement. In my opinion,
it has to be a single photon emission, because we inject a single electron. There can be just one electron at a time, because if you inject the electron and populate this defect state, there is just nothing else around that you can populate with electron tunneling. And also, if you just by energy conservation, also you see that the whole kind of kinetic or like potential energy, like the energy difference between injection and initial and final state, this exactly matches with the photon energy that comes out. So in my opinion, it is trivial that this is a single photon, a single electron conversion into a single photon process. We would love to do the G2, but we don't have enough time, not enough counts. Okay, how is this different? I think it's very different from an optical excitation, because there you first of all always study a charge neutral system. In our case, we inject an electron and perturb this heavily into this discrete state. Now for optical excitation, you would actually have lift or doing an excitation of your electron at your defect to another state at your defect. So, and there you would of course expect to see more narrow line widths. But in our case, it's really a combination of some tip property and some defect property. But that's something we want to do, and also that our collaborators have done in the meantime, to look at signatures of individual sulfur vacancies that can be attributed to really just this type of defect. So to look at optical luminescence from those, by again selectively comparing, by selectively introducing this particular defect into our sample. So I would suggest looking into the literature of this whole Leitner group, and there you might find and some interesting results.
There's another question in the chat by Rishabh, which is how is the RE plus doping perform? Co-evaporation during the growth of the TMD or later?
It's co-evaporation. So I think, as I understood, so again, this was not done in our group, but at Penn State. So they have this vapor transport kind of mechanism in this MOCVD, and they can just by some mass flow controllers, they can dose different amounts of this precursor vapor into your cells. So they have a very controlled amount of precursor that they can deposit. So during the growth bottom up.
Great, thanks. And now there's a question by Abdul. Please go ahead.
Yeah, I have actually two comments. So back again to lifetime of these phonon peaks. So are you saying that the widths doesn't change really with energy? So could that be, I mean, it does, but maybe, yeah. So could it be just the lifetime is limited by interactions rather than intrinsic lifetime of the states? That's my first question.
So you would,
yeah.
Okay.
Well,
so maybe let me answer first one before I forget the second one.
Okay.
So you were saying that you would expect an increase of the width with energy.
Right. Right.
Why is that?
Well, I mean, it's just like the Fermi liquid case. So when at higher energy, you have a shorter lifetime of states, perhaps, and so you would expect that if the lifetime doesn't change, then probably it is limited to interactions with other process that is really controlling the lifetime, not as the intrinsic width. And so in that case, you should not see a difference so much in them.
Yes, so at least in our model, we are assuming a constant width. And I agree that it's probably because of the small overlap between your defect state wave function and your graphene below that will also facilitate the tunneling of your electron then eventually to the substrate.
Okay, so that's probably the case. The second is after you bombard, let's say the case was a helium bombardment. Have you ever combined it with annealing? Did you see any self-organization of these defects somehow, or they're still sporadic and they're cannot be manipulated by annealing?
So we haven't tried this extensively with the helium ion bombarded one. So what we have seen in the other sample, where we just anneal, is pretty much an stochastic distribution. So it was pretty random. So there was not like a line defect forming or something like this. I think in general, the mobility of defects is fairly low. Okay. There is covalent bonds and so on. So I mean, at the end, we don't know, but since the distribution is stochastic in all the samples where we introduce these defects, I would expect that there is a very low mobility of these defects.
Okay, thank you.
There's another question by Leo. Leo, please go ahead.
Yeah, hey, I also had a question to the last part, the luminescence. And probably you said it and I just missed it. So is that a charge defect you're investigating here? And did you investigate neutral and charge defects?
So this one is a neutral defect. But of course, you're always then attaching the electron. Your final state is kind of an ionized state. But we didn't look into the difference between charged and decharged. I mean, that's something which is fairly interesting with these materials, because through gating, in principle, you can change the Fermi level. But we haven't established these devices yet. But that's something, of course, which is on the high priority list for us, to changing the Fermi level, and by that changing the occupation of the charge states. That's something we want to do. And also investigate, I mean, that's what more your first question probably was going into. We want to also introduce decoupling layers in between. So we are working right now on HBN samples, which are multi-layered, where we can grow then the TMD on top. So to really extend the lifetime, and hopefully also study then the luminescence, which is only coming from our material and that does not involve the tip. So for instance, injecting straight in the TMD and then look at the transition now. So that's something we want to do.
Yeah. Yeah, good, cool.
There's another question in the chat by Rishabh, which is if the CH4 plasma creates CH defects through substitution of chalcogen, or it prefers to bind to an already vacant chalcogen site. Any preference for the defect reaction pathway?
I think it's hard to say. So what comes, I mean, so certainly everything. So what they do is, let me see. So here, I mean, that's just a cartoon, of course. So even the plasma, you have many reaction products in there. So you expect to have CH3, CH2, and whatnot. So it's fairly complicated. We haven't done a simulation or anything on this. So, okay, what comes first? At the end, I don't know. So what they don't do, it's not a stepwise process. So they don't just anneal, make vacancies, and then put the carbon in there, but everything happens simultaneously. So they do this at elevated temperature. So probably maybe you need the formation of sulfur vacancies first. I could see why this would make sense. And then this becomes a very preferred binding site, of course, for this carbon atom. At the end, I would say I would leave it open. So I'm not 100% sure, but I think the suggestion makes sense that you maybe need first a few vacancies to form and then have the carbon stocking there. So this is done at elevated temperature, the CH4 plasma.
So you also heat the substrate, the TMD substrate, while doing the plasma treatment, is it?
Yes, but then also to make the plasma, I mean, everything is hot already. So I think it's hard to do it without it, I would say. Okay. So I think it's hard to decouple. One could probably cool the sample at the same time and see whether it's still effective, but we haven't done that.
Okay, so in your experience, do you see any difference in, statistically, the difference in the number of sulfur vacancies and the CH vacancies that you grow on top, like before and after the treatment of the TMD? So is there any statistics on that?
So there is no, like in the other samples, which we don't heat in UHV deliberately, there is no vacancies to begin with. So if we don't do this, so we see a few of these carbon impurities at our sample, but there is no vacancies. The same thing, if we do that, there is no vacancies. So I think just vacancies in air are highly unstable. So they're dangling bonds. They want to be saturated with something. And I think they just grab whatever. They grab oxygen from water or O2, or maybe they grab carbon from some adsorbate or so on. So we don't see any vacancies in these samples. So we only see vacancies if we anneal to high temperature in a UHV environment. If you do it at ambient, I'm pretty convinced that you will still not see vacancies because they just want to be saturated.
Thank you. Very nice results again.
Sure, thank you very much.
There's another question by Alexis in the chat, which is if you tried STM's luminescence with a silver-coated tip, which has a sharper plasmon.
Silver-coated tip, we, let me think, we did that. And the plasmon, the enhancement looked fairly similar to us. So we didn't do a lot of statistics. How this, especially, so what interested us was especially this cutoff frequency, because this should be also depend a lot on your material. And I think it's fairly similar. So we have this in the supplemental material of this paper, where we also tried silver tips, but it didn't seem to make a huge difference.
And there's another question by Leo. Leo, please go ahead.
Might be a stupid question, but so in your sample preparation for the graphene layer, do you have to contact that somehow? Or is that always through the silicon carbide? Does it find like some, I mean.
You mean electrical contact?
Yeah,
or?
I mean, you do STM, but there's silicon carbide under the graphene.
Yes. Yes, so
you have a contact on the graphene flake, or is there somewhere a hole anyway where you get the current through?
Correct. So no, so silicon carbide is complete. I mean, there is different forms of silicon carbide. You can have it doped or undoped, but usually it's semi-insulating. So it's basically for STM, you cannot do STM on silicon carbide. It's an insulator. But then you can grow epitaxially this graphene. So this is not flakes. So this is wafer scale growth. So we do it in a kind of a growth chamber where there is carbon around 1600 degrees. You basically evaporate off the silicon, so you have a continuous layer of graphene, single layer or bilayer graphene, and we contact this on the side. So that means our electron has to actually go in a fairly conductive layer between the tip and the contact on the side, which is a few millimeters. And to me, it was surprising that this worked. So just by mechanical contacting with molybdenum clamps, this works surprisingly well. I would think you would just destroy your graphene below, but it works 100% of the time, and that's a very cool thing. And the nice thing about this graphene is really it's conductive, but it doesn't like adsorbate so much. So you just annihilate at 200 degrees or so in vacuum, and you get rid of everything. So I think this was one of the key kind of points in these developments that we figured out that this is really a useful platform to putting these 2D materials on to make it really compatible with STM.
All right. I think we can stop at least the official part here. So I'll stop the recording. Let's thank Bruno once more. Thanks. It was a really nice talk.
Thank you very much for attending.
Thank you.